Welcome to our 418 final project video on data parallelism in neural networks. So off the heels of Tianxi's final lectures on distributed and deep learning, we wanted to explore model and data parallelism, specifically in the context of image classification. So we wanted to see how previous results from folks at Google Research, namely that increasing batch size resulted in a decrease in training time, and whether or not this result would hold in the context of incorporating message passing or shared memory into neural network training. So specifically, we used a simple feed-forward network. We used a more complicated basic, but still basic CNN, and a much more complicated CNN known as ResNet as our three models. And we incorporated message passing and shared memory in both Python and C++. So first, we're going to talk about how we did this in Python. Specifically, we used a package called MPI4PY, which is just a message passing client for Python. And what we did was, after coming to a pretty simple serial implementation using PyTorch, we decided to incorporate message passing by having a master process have a copy of the model, and by copy we mean a copy of the weight matrices, and then it sends this weight matrix to all the worker processes that are spawned. Then we also send along a portion of the data, and each worker process would then compute and update their weights through training on that specific portion of the data. Then they send their updated weight matrices back to the master process, which combines them, and then we finish one iteration of the training loop.
Meanwhile, in C++, we use the shared memory approach through using OpenMP. And what we did here, again, it was data parallel, but instead of having a master and worker processes, we used OpenMP to distribute the load among threads uniformly. And what we would have is for each thread would begin with a randomized sort of weights and stuff like that at the beginning of the epoch. And then throughout the epoch, each thread would have a certain number of data samples assigned to it that it would train on. And then at the end, it would aggregate the results in this shared weights array that you can see at the bottom there, using atomic for synchronization over that shared memory.
Now we're going to talk about some of our results. Specifically, when we look at the top left, these are on our baseline models. And what baseline here means is we didn't use any message passing or shared memory. So these are our very simple feed-forward multi-layer perceptrons and our convolutional neural nets, or CNNs, without any fancy layers. So what we found here was that when we doubled the batch size from 32 to 64, we saw almost a half reduction in training time. This is very consistent with what the Google researchers found. But once we go from 64 to 128, then we see a smaller reduction in the training time. Again, very consistent with what the Google researchers found. But when we incorporate message passing in our very simple CNN, we saw that the decrease in training time when we increase the batch size is present, but at a lower degree. Specifically, due to the overhead from sending all these messages, specifically the large weight matrices, we saw that the increase in batch size was still enough to reduce the training time, but not enough to result in the specific linear reduction in training time that we were accustomed to seeing without message passing. Additionally, we see that increasing the batch size results in lower accuracy. This is a common phenomenon throughout neural networks, simply because the higher the batch size, the poorer the generalization, i.e. the poorer the testing accuracy of the resulting neural network.
In shared memory, we saw a very interesting pattern where we had a big speed up from 1 to 4 processors, 1 to 4 batch size, and a pretty good speed up from 1 to 16. But after that point, we saw an inverse trend where we actually received some slowdown. So it seems that this method is only efficient and only useful up to a certain point, after which it actually becomes detrimental. And the reason for that is because during the spawn of each thread, there's a very high amount of overhead, both in terms of computation due to the synchronization primitives that we have to use over the shared memory, but also due to the individual memory that each thread has to have allocated to it. And the randomization process, which is also a bottleneck on each thread and a bit of computation overhead. The memory overhead becomes a problem because when you have such high competition over RAM during the process, due to intermediate calculation arrays being spawned for each thread, what you get is high amounts of fragmentation in memory, leading to worse cache efficiency and overall a detrimental effect on speedup.
Yeah, so this has been a quick recap of our project. For more information, please refer to our write-up, and thanks for listening.